This is GCSE Physics, Electricity Lesson 18, and this one's electrical power. I'm going to utilise a new equation in a couple of questions, P equals I squared R. And we do several equations that we've been using already in previous lessons to solve more complex problems. So basically this is maths heavy. There's lots of problems to solve, so let's crack on with it. So in terms of equations, we're going to be using P equals IV, which we've used in previous lessons. So power is measured in watts, current is measured in amps, and voltage V is measured in volts. Then we've also got energy is power times time, energy in joules, power in watts, time in seconds. So we've used them previously. And then a new equation which we're going to use in a couple of questions today is power is equal to current squared times resistance. So you want to make sure you've got this one down. So power is measured in watts, obviously. Current is measured in amps. And resistance is measured in ohms. So let's make a start. So there's going to be lots of practice questions. I'm going to put two on at a time. I just want you to pause the video, have a go at them, and then I'll take you through the answers. So the first one, calculate the power of a kettle that uses 7.2 megajoules of energy in 120 minutes. So what we need to do is use energy as power times time. Rearrange to get power, so that would be energy, and then we need to get rid of the times time, so divide by time. So energy divided by time. So energy is 7.2 megajoules, which is 7.2 million. Which is 7, 2, and 5 zeros. Divided by time of 120 minutes into seconds, so that's 120 times 60. Which is 7,200 seconds. And if you put that in your calculator, we get 1,000 watts. So next one, how much energy does a kettle of power 1.5 kilowatts give off in 3 minutes? So energy is power times time. So the power is 1.5 kilowatts. If you times by 1,000 to get 1,500 times the amount of seconds in a minute is 60 times 3, which is 180 seconds. So that gives us 270,000 joules, or 270 kilojoules. Right, let's do some more. So if you want to pause and have a go at this one. Calculate the power of a torch bulb that requires a current of 200 milliamps for a voltage of 6 volts. So that'll be P equals I times V. So the current is 200 milliamps. Remember, we need to divide it by 1,000. So we need 200 divided by 1,000, which is 0.2 amps. So we've got 0.2 amps times 6 volts, which gives us a power of 1.2 watts. Next one, calculate the current drawn when an electric clock of power 20 watts is connected to a 230 volt supply. So again, P equals IV, but this time we want current drawn. So we need to rearrange, we need to make I the subject. So the easiest way to do that, we've got times V. So to get rid of a times V to the other side, we need to do the opposite and divide by V. So power divided by voltage will give us the current. And then we just need to do 20 divided by 230, which gives us a current of 0.087 amps. Let's do some more. So let's pause and have a go at this one. Calculate the power supplied when a current of 50 milliamps flows through a 2 kilo ohm resistor. So that's the new equation. So that's power is equal to I squared R. So the power is simply the current squared. So we've got 50 milliamps, so we need to divide that by 1,000. So 50 milliamps divided by 1,000 will give us 0.05 amps. And then we need to square that, so power is equal to I squared R, so 0.05 squared times the resistance 2 kilo ohms, which is obviously 2,000. So if we calculate that, we get a power that's equal to 0.25 watts. So have I got the next one? Calculate the current flowing when a resistance of 3 kilo ohms gives off a power of 2 megawatts. So this is a tricky one, this one. Power equals I squared R. And what we need to do is rearrange this to make I the subject. So we need to first of all get rid of the times R. So the easiest way to get rid of the times R is to divide, well, the only way is to divide by R. So P divided by R is equal to the current squared. And then once we've done that, once we've done power divided by resistance, we can just simply square root. So the power is 2 megawatts, which is 2 million. If you've done standard form, and you know that you can write 2 times 10 to the 6 instead if you wish, so 2 with 6 zeros, divided by the resistance of 3 kilo ohms, which is 3000, or 3 times 10 to the 3. And then we need to square root that to give us the current. The current value is 25.8 amps. If you've written 26 amps, that's fine. If you got that one well done, that's a tricky one. Let's move on and do some more. By the time we finish these, you should be an expert. So next one, let's calculate the power. So we've got energy and time. We need power, so that should be energy equals power times time. So power will be energy. We need to get rid of the times time, so we're going to divide by time. So power is energy divided by time. So the energy is 90 kilojoules, so 90,000 divided by a time of 3 minutes. So 3 minutes times 60 seconds is 180 seconds. So that gives a power rating of 500 watts. Next one, so how much energy does a light bulb give up? So we've got 150 watts and 2 hours. So energy is power times time. So the power is 150 times the time of 2 hours. So we need to do 60 seconds times 60 minutes times 2 hours. And that will give us the amount of seconds in 2 hours. So we can just do that. Put that in our calculator, which gives us an energy of 1,080,000 joules. Or you might have written 1.08 megajoules, which is obviously fine as well. Let's do a few more. So this one, if you want to pause and have a go, calculate the power of a television that requires a current of 30 amps and a voltage of 12 volts. So it's really straightforward, this one. P equals IV. So the current is 30 amps times 12 volts, which is 360 watts. Next one, calculate the current drawn when a cooker of power 4 kilowatts is connected to a 230 volt supply. So again, P equals IV. So we need to get current, so we need to get rid of the times voltage. So we're going to divide by voltage, so power divided by voltage to give the current. So we've got 4 kilowatts, which is 4,000 watts, divided by a voltage of 230 volts. And that gives us 17.4 amps. A few more to go. Let's pause and have a look at this one. Calculate the power supplied when a current of 250 milliamps flows through an 8 ohm resistor. So that's the new equation again. P equals I squared R. Just got to be careful this one. 250 milliamps, so we need to divide that by 1,000, which gives us 0.25 amps. So we need to do 0.25 squared times the resistance value of 8, which gives us 0.5 watts. Next one, calculate the current when we've got a resistance of 0.5 ohms and a power of 500 milliwatts. So the 500 milliwatts is 0.5 watts. So again, power is I squared R. So to get current, we need to get rid of the times R. So power divided by R equals I squared. And then once we've done power divided by resistance, we just need to square root. So the power is 0.5 divided by resistance, 0.5. So 0.5 divided by 0.5 is 1. And then the square root of 1 is 1. So the answer is 1 amp. Okay, one last one. So let's pause and have a go at this one. Final one, calculate the resistance of a component when a current of 50 milliamps flows and a power of 200 milliwatts is produced. So we've got 50 milliamps and 200 milliwatts. So we need to divide them both by 1,000. So we've got 50 divided by 1,000, which is 0.05 amps. And then we need to do the 200 milliwatts, so 200 divided by 1000, which gives us 0.2 watts. Now we need to do power equals I squared R. Now we need to get resistance, so we need to get rid of a times I squared, and the opposite of timesing by I squared is dividing by I squared, so power divided by I squared will give us the resistance. So the power is 0.2 divided by 0.05 squared, and that will give us the resistance value, which is 80 ohms. Hopefully that went okay. A bit of a long one, lots of calculations, lots of good practice there. So you should be able to do just about anything of that ilk that comes up in the exam. So thanks for watching, and I'll see you at the next one.